Okay, I kind of rushed through the last problem. I apologize. I want to come back. I have a 15-minute limit, and if I really don't finish the problem within 15 minutes, then pretty much I can't upload it in YouTube. So let me do this part again. I was rushing through. I said if I was to look at this in the direction of y, y would run from 0 to y equal 2. And then x would run from that right there. If I want to solve this equation for x, x squared equal 1 minus y minus 1 squared, and x would equal plus or minus the square root of 1 minus y minus 1 squared. And in that, this is 1 minus the radical, and this part is 1 plus the radical. So this will run from 1 minus the radical of 1 minus y minus 1 squared, gives it out of 1 plus the square root of 1 minus y minus 1 squared. And there it is. Now I want to look back at problem number 4. Again, visualizing is a must. You really don't need the graph. It's not going to say graph in front of this volume. It's going to say write 6 different iterated triple integrals for the volume in the first octane enclosed by the cylinder. Evaluate one of the integrals. So you could do one of those. That's not that hard to do. The problem is setting up the integrals. And if I would go ahead and talk about what this is a cylinder. This is really one of those, and it runs infinite because there's no y, right? And it's cut off by x equal 3, the x-axis and the y-axis. So in reality, this is really what it looks like. It looks like you're gonna move 2 units and 2 units, and that's the cylinder. And you're gonna move 1, 2, 3 to the right, 2 units out, 2 units up, and it's gonna look like a quarter of a cylinder, literally. Alright, so let me take this and throw this underneath it. Now, I have 3 ways of finding this volume. I'm going to write all 3 ways. Each way consists of 2 different triple integrals, and let me get that started. That's the first. Or I'm spacing those. So the first, I'm going to do what we normally like, and that is if I run the insidemost integral with respect to z. What that means, I'm looking at this from the top down, and you always run kind of like a laser beam. It always runs from the negative to the positive. Do you see that you're going to start by crossing z equals 0, and you're going to exit out of this top, and this top, it's really x squared plus z squared equal 4. So z squared equal 4 minus x squared, and z will equal, it should be plus or minus, but since you are in the first octane, this is z equal the square root of 4 minus x squared. But if that's how you're looking at this, then this is really what you see. If you look from the top down, do you see that the only thing that we're seeing is along the x-axis 2 units to the right, along the y-axis 3 units up, and you're looking at this rectangle. And now, can't I find the area of this rectangle 2 different ways? Let's look a bit better. Come on. So again, if I'm glancing at this, I am in the first quadrant, and x runs to 2, and y runs to 3, and that's all you see. If you go high enough and you look from the top down, the only thing you see is the 2 dimensions. You can't see the 2 dimensions, right? So when you look down, well, can't I say, you know what, I'm going to run this from x equal to x equals 0 to x equal 2, and that means y runs from 0 to 3. Or you could say, I want to do this sideways. I want this from y equals 0 to y equals 3, and that means x runs from 0 to 2. There it is. I'm going to get rid of this. I really don't need this. I'm going to leave this for this first problem. The second problem, I'm going to write a bit smaller. And I'm going to say, well, I could have did this differently. Leaving some space for the graph. I could have looked at this, and let's say I looked at this first in the direction of y. Well, in the direction of y, now I'm looking at this from negative, oops, that's x, forgive me. From negative, and this is y, so from y, it's going to come in and hit from 0, and it's going to exit out of y equals 3. In that sense, I'm looking at this graph from the y direction, and from the y direction, this is what I see. This is x, this is y. The only thing I see is this quarter of a circle. And I could do this two ways as well, right? I could say, you know what, I'm going to run this from x equals 0 to x equals 2. That's not a y, that's a z. I'm going to run this from x equals 0 to x equals 2. That means z runs from z equals 0, and doesn't z exit out of that circle? If z squared plus x squared equals 4, doesn't that mean z equals the square root of 4 minus x squared? Or somebody might say, well, forget that, that's not how I want to do it. I really want to do this. I want to run from z equals 0 to z equals 2, and then y now is going to run from, not y, x is going to run from x equals 0, and it's going to exit out of this equation. Well, if I take this equation and solve it for x, wouldn't that be x equals the square root of 4 minus z squared? And somebody will say, you know what, forget that. I don't want to do any of that. I want to look in the direction of x. Well, okay. In the direction of x, if I look at this in the direction of x, what do I see? In the direction of x, I'm coming from there. Isn't that going to hit the first 0? And wouldn't that exit out of the actual cylinder? And isn't the cylinder right there the square root of 4 minus z squared? And now what do I see when I look at the 2 dimensions? When I look at the 2 dimensions, if I'm looking at this in the direction of x, there is no more x. There's y and z only. Well, let's see how does this work. This is y, this is z. Well, I notice y runs all the way from 0 to 3, and z runs all the way to 2. If I look from the back, from a far distance or the front, isn't the only thing that you see is a rectangle? Isn't this right here? This right here? And this part that we saw on the floor, the rectangle on the floor, that was actually this right here. And this part that we saw is really right here. And isn't the area of this very simple? Can't I say, you know what, I'm going to run this from y equal, remember, y take the place of x, from y equal 0 to y equal 3, and that means z is going to run from 0 to 2. Or I could say, forget that, I'm going to have z equals 0 to z equal 2, and y is going to run from 0 to 2. And there's 6 different ways. Any one of those you integrate will give you the same result. That's a lot of work, and that's the bulk of this chapter. Actually, believe it or not, number 4 is among the longest of these problems. The rest of the problems are not as long as this right here. So, this is one lecture on this. I'm going to do another lecture on that and combine it with another portion for next class meeting. For now, you're going to do the homework. This is section 15.5 on page, again there's more, on page 929. And you're going to do numbers 3 through 17. Odd, not to worry. 3 and 5 are the only ones like that. 7 to 17 you're integrating. I'm going to make sure that you start practicing your integration a bit more. Again, I'll wrap this section up next time. We're not done with this section.